Ladies and gentlemen, dear students, thank you very much for the invitation to come to here. It's a pleasure, in particular on such a nice day like today, to go through, to drive through. And I intend to do together, it will be really an experimental session to do the experiments on that singing rod. And the next thing I would like to, maybe a girl student and a boy student, to come to here and participate for all the others, and they can then pass on details of what we are doing. But I would like some of you really to participate here on the stage.
여기서 장학생 3명하고 여학생 1명 이 올라가 직접 시점을 같이 해볼 학생.
I am very happy to see that. I'm very happy to see that because
Where's your little bag?
because I expected the opposite. I expected that nobody would come, so, but okay, this is nice, so we can get started. But we need our equipment. Yeah, I have to orient myself, sorry. I have to see where the rods are. Maybe my secretary will know, but she is not here at the moment. Here we go. Colifornium. We can put it into some corner here. I think it will not hold if we leave it. Yeah, this is a good place.
Which material will you go first?
Aluminum.
Aluminum. Here.
So this is the first rod we will be looking at. It's a rod from aluminum, pure aluminum. And what else should I say about it? You can get at a hardware store, you get it for, let's say it in dollars, the common language, common currency we know. You can get such a rod at a hardware store for maybe a few dollars. Somebody will translate? Do we always translate, or should I continue speaking English?
Shall we go without the translation?
What is
Without
it?
the translation, can we go?
Yeah.
잘하면 되죠? 잘하니까
Yeah,
They understand all.
understand what you say.
Wow. Without the translation, they can understand what you say.
yeah. I expected that. Okay. Okay, I started saying you can get this at the hardware store for a few dollars, and all this, what we need for these experiments for this afternoon, you almost probably all have that already at home, or you can go at the hardware store and also buy such a rod and other rods. We will also do experiments today. So this is a very convenient, I mean, I assume that most of you have a laptop available, and the computer program which you need on the laptop is Audacity, is also free to have. So virtually I would like to introduce to you some experiments which you can easily do at home, and I hope you will also find, like myself, that they are very interesting. And many things are not yet resolved. So this is also a challenge to find something about acoustic and to learn more about this field. Okay, so what is so particular about this rod here? In order to show you that, I have here some colophonium, which people who play violin also know very well, because you have to treat the violin bow with some colophonium in order to get the sound from the string. And I would like to introduce you to the sound of the singing rod, which I get also by using colophonium. That's the wrong one. Well, try another one. I'm not yet satisfied. I would like still to try another one. You hopefully heard a little bit of sound, but this is not the best we can do. You have to support it. You support it with one hand just in the middle, at the center of gravity, and when you have done that, with the other hand, you rub along the surface.
Yes.
He's coming.
Yes. There we go.
I think I better retire. You do that much better. Okay.
There we go.
Wonderful.
Rest of the aluminum. Yeah. Yeah.
I leave it to you. Okay, so you can hear the slightly different frequencies. It's a pity that this didn't work, because that resonates at a slightly even more different frequency, and that would have been spectacular. Okay, so I do not want to treat you. I hear the protest. Yeah. I know that this is some slight protest against too much mathematics. I could also introduce it by saying, by classical theory, you can understand the singing rod in the following way. You have seen we pull the rod, we pull, try to make it somewhat longer, we pull it. At the same time, there is a force which wants to pull the aluminum rod together, and by this computation we can calculate the frequency. And then it turns out that what we just heard, the frequency, the sound we just heard, can really in the frequency be calculated by that formula. And more I do not want to say about that formula, not to bother you too much with mathematics, although mathematics and sciences is definitely very important, and the quantitative understanding otherwise not possible. Next slide, please. I do that myself. Okay, so what you should also know in order to understand what we are doing by getting that music from the rod is the so-called slip and stick technique. When you try to strain this rod by pulling on both sides, then what happens with the rod is called so-called slip and stick technique. It rests still for a while in the old position, it doesn't do anything, but then suddenly slips. That you see here is a strain stress curve of the rod. When we try to strain it, then we pull on both sides, but the rod will not immediately react, but it will slowly react and make a jump. So you see a slope there of the curve, then it jumps, and at that moment the rod jumps in his length and gives the sound. And this is the acoustic signal. In fact, when we look in detail, then we see maxima here, then for quite some time nothing happens, there's a straight line, and then is again a feature, and this feature indicates that we get the sound at this point. This is plotted versus the stress which we apply to the rod, and at some point then it slips, and then we get also the acoustics. Not concerning not our rod, but the similar system. This is meant to be all violin or guitar strings, and the various oscillations in guitar strings. Guitar strings can be excited in the same way as we do with the rod, only there we take a bow and play the violin with a bow, but it is also that stick and slip mechanism which we use. Now that lower part indicates to you how the signal from the rod is transmitted. You have to imagine that due to the sound wave we get areas of compression. These are the dark lines here, and in between get areas of decompression. You will see that in a moment more clearly. And these, via the pressure mechanism, I can indicate it like this. So what the wave does is propagate through space in the air, and the wave fronts of the wave have a motion like this while the wave propagates. The so-called longitudinal wave, and our oscillations, the waves which we see in the singing rod, are also of that kind, and they propagate through the air like this, as indicated. Next, please. Okay, so the mathematics which I introduced to you, and you protested a little, give the result which is shown here. We have only to look at the upper part, at the upper formula. That is, which has been worked out by the mathematicians for the singing rod frequency. It's given by the formula as is shown here. Essentially, we have a square root of elastic module by the density of the mass density described by the rho. And without going now into the details of this mathematics, I will just make the statement that this has been proven by the experiment, and this formula has been found to be correct. Okay, next please. To give you an understanding, this is a qualitative understanding what happens during one cycle of the oscillations of the rod. The rod material oscillates between a high mass density, so where the material is compressed, indicated here in red, and neutral part, no extension or shrinkage of the material. That is, the neutral part is white here, and then on the other side, back from the observer here, is the decompressed state. So there's the mass density is lower, here it is neutral, and here is higher than normal, than compared to the neutral case. And now you can see this, when we further on go from one status of the rod to the next, is indicated here. The red area has become a little less red, and the blue has also become a little less blue. In the middle of the neutral state is not changed, it is still white as here before. And then we go on to the next set is here. This is here down. Now the red area, the compressed area, has become really less compressed. You see on the pale color, it's not so red anymore as here. And the blue has also become weaker. So it all goes towards the neutral state. Now finally, in the middle between these cycles, we observe the real neutral state. As you see here now, it's pale and white all along the whole rod. There's no change in color more. So the increased density and decreased density has disappeared in this moment when the rod swings through this status. Now, going backwards, the same kind of thing happens on the other side. So now you can see, now this side becomes blue, that is less compressed, and the other one becomes red, that is more compressed, and that goes on until we have now just the opposite of this one. The red is now on this side, finally, and the blue has arrived on the other side. So this is what the rod does now during one cycle of its oscillation. And to give you an idea how fast that oscillation is, that is on the order of corresponding to some kilohertz in the frequency. So a millisecond or something is the length that it takes to go from here all through the different phases to the other side, and then the same kind of thing happens backwards and it swings back and forth like I indicated here with the laser beam.
여기 보여준 거는 빨간 부분은 덴시티가 높은 데고 파란 부분은 덴시티가 좀 얕은 데고, 그러니까 로드로 한 곳은 압축이 되고 한 곳은 늘리고, 그래서 그게 이제 사이클을 이루면서 소리를 이제 왔다 갔다 하면서 진동 프리퀀시 맞을 때 소리가 난다는 그 얘기 하는 거예요.
You can do that. I think this is the copper. But copper is interesting anyway. 2, give 1 copper. Maybe
아까는 알루미늄으로 소리를 냈는데 지금 이제 알루미늄이 아닌 다른 머티리얼도 똑같이 사용하는 것을 이거는 그 알루미늄이 아닌 구리로 하는 것을 보여주고.
This is a beat. 2 frequencies which are very nearby interact, and then you have this. It becomes louder and slower, louder, periodically. It's called a beat in music, when 2 frequencies are very narrow. Now maybe aluminum and brass. If you take the brass.
물질에 따라서 그 라디의 모양에 따라서 이 프리퀀시가 다시 나오는 거예요. 그래서 두 개가 같이 있을 때 하모니가 이루어가고 뒤에서 이루는 것을 하는 것처럼, 그러니까 지금 모양이 다른 거, 물질이 다른 거를 하면서 그 피치가, 그 프리퀀시가 서로 다른 소리가 나오는 거를 보는 겁니다.
For a long time it was believed that this is a phenomenon which occurs only for metal rods and not, for example, for insulators or other materials like wood. And I'm very proud to be able to announce that with my group, my co-workers, we found that the phenomenon exists also for wood, which is non-metal, and so there seems to be some kind of breakthrough in the knowledge about this singing rod mode. And now let's see. Yeah, I think we take the first to wood now. The other one is even more difficult.
옛날에는 처음 할 때는 메탈에서만 나온다고 생각하고 맨 처음에는 알루미늄에서 나온다고 생각했는데 아니고 다른 메탈 나왔는데.
Maybe go to the mic, next to the microphone.
나무, 유리 이런 데서 이제 똑같이 나온다는 얘기입니다.
The point here is that you hear the sound, although my hand is already gone, not in touch with the rod anymore, but you still hear the sound. This is a new phenomenon also for the rod. So wood then is a particular case. And let's hear the wood, the sound from the wood. Has everybody heard it? And what did you notice? I talked about this ringing sound before, that it goes on when I finished already my stroke. You still hear the sound. That was the case for the metal. And what do you, when you observe him, and he plays the rod, do you still have the ringing? Do you still hear the sound when the stroke is already over? The most difficult case which we met up to now is this as often an insulating material. And can you try to get the sound from that one? Ah, there was something. Yeah, very nice. So again, such a case where the sound immediately dies out when the stroke is over. That seems to be typical for these insulating materials. Okay, now I have to see what else we have in our program.
달 같은 경우는 아까 한 것처럼 치고서 쭉 빼고 한쪽에서 진동이 오래 가잖아요. 대신 이제 우드나 인슐레이션 같은 경우는 그 잔향이 오래 안 가고 금방 끊어지고 하는 게 특징, 그 물질의 특징이고.
Can we go to the next? So I explained already this phenomenon. The oscillation consists in a zone of higher density which goes from one side to the other during one complete cycle. The red, higher density of mass is present here, but on the other end of the cycle, this is the density is lower for that side, so this goes back and forth. And now we have another presentation of this phenomenon. Here you have a somewhat more accurate but not so complete presentation of this. And that is here. I talked about, where is it? Yeah, I talked about a node in the middle and maxima of the oscillation on both sides. If this is the rod in that situation, then we have to follow this one. Antinodes at the end of the rod, large displacement, but that is a density, that is not a local displacement like one could think, but represents the density of the material. And in the middle then is neutral, there is no displacement. And on the other side then we have the same negative. So that we see was red and blue in the previous slide, just for the understanding. Now this picture also reminds us that this singing mode rod is not the only one. There are other oscillations which I did not mention up to now, but one also has to consider for completeness, and they are indicated here. the interpretation is again here for the one which we discussed up to now, one node in the middle, no displacement, and maxima on both sides of the rod. This is one maximum displacement, and this is the other nodes and antinodes across the whole length of the rod. Phenomenon in wooden rods, which I showed you, where we do not have this oscillation, when the hand which pulls the rod has left already the rod, it simply decays out. That is due to other properties of the material, like wood has other properties of aluminum. And one reason why it has other properties is the stress-strain curve here, shown here. So the interpretation now is, or the suggestion, when the material's properties are connected like this, when it is stressed over strain curve, for example, goes like this, linear up to a certain point, and then comes back in the same way, then we have the condition for no energy dissipation, and then we get the ringing after the hand has already lost. Then it basically, theoretically, could ring on and on in all eternity, will never stop, but of course practically this is not possible, and we get this. But when the material, when the stress-strain curve shows some deviation, like here, goes off from the straight line, and now we go back along this curve here in a full cycle, which is described by one going around here. In a full cycle, we have now an area enclosed which represents the dissipative energy, and now the system loses energy to warming up of the sample. And that is then the explanation how the process goes when we have an insulating material like wood. You heard already the various rods. In fact, we had aluminum, we had brass, glass I did not show, but glass behaves like a ringing system. So here in glass we have also this phenomenon, and it rings, as you can see from that plot. Okay, we have put all these data together, the ones which we measured, of course, only in that table, and I said already, essentially it agrees with the theory. What we observe here and measure as far as the frequencies is concerned, but as far as the intensity and the loudness of that phenomenon is concerned, seems to be still a puzzle. And now, in the following, I would like to make a suggestion, knowing various other phenomena, like sound is, for example, like in a hall, like this one here, sound investigations and what is reflected from the walls of that hall and so on is a very important aspect, and there we can draw some knowledge which might also explain the phenomena which we observe in these rods. And such knowledge is around, sometimes in a way that it disturbs measurement, and a well-known case where ringing, for example, is not welcome is in electronic parts where we have large amplitudes or nuclear magnetic resonance, which is used to make investigations of the body. There, such phenomena are not welcome, and one is ringing that is described or occurs. Now, you see here, this is meant to be a strongly increasing signal in some electronic part, and that is known to result in such an oscillation of the intensity, which comes only from this high amplitude, this low small change in the electrical signal at some point, and then leads to this oscillation of the voltage. So this is not very welcome. It's related to what we have seen in the singing rods. To come finally to an aspect which is probably also standing behind this hall here. This hall, such halls like here, they can have a well-known good acoustic, and then these properties are optimal for the application which is in mind, or they can be on the negative side disturbing, and that I would like to address in the following. Suppose we have a plot here, which means that for some, this is a function of time here, in some hall we have increasing acoustic signals because, for example, there are many people, much equipment, then the noise level in that hall increases until the performance is over, and then decreases again, and these conditions can be changed by the proper architecture, like shown in the next slide. Person here, another person sitting in the audience here, like similar in a present situation. Then it's not only the direct sound which is being heard by the audience or the performer himself, but there are many ways to reach acoustically the audience, which is indicated here, the direct sound, and that is the same kind of after noise signal which is also present when in the singing rod the intensity dies out. Then we have a similar situation. What is left over can excite new oscillations.
우리가 말하는 거는 여러분들이 강단을 내리면 교수님이 말을 하면 여러분들이 귀에 직접적으로 들어가는 소리보다는 딴 데 들렸다가 오는 소리가 많잖아요. 그 소리가 많은데 그 소리가 지금 같은 경우는 우리가 여러 가지 소리를 다 적절히 들을 수 있지만 싱잉 라디오인 경우에도 소리가 처음에 나왔다가 이 라단에서 반사가 되고 그리고 반사가 되면서 자기가 딱 맞는 음들은 반사된 것들이 같이 맞아서 소리가 커지고 어떤 경우는 서로 이 간섭이 잘 안 돼가지고 없어진단 말이에요. 그래서 이와 같이 해서 싱잉 라디오의 소리가 크게 나는 이유는 반사된 소리하고 처음에 생성된 소리가 서로 잘 맞는 경우 소위 말하는 레조넌스라는 얘기예요. 레조넌스. 한국 말하면 공명이라는 말이죠. 공명이 일어났을 때 싱잉 라디오 소리가 크게 난다는 얘기예요. 그래서 이 리버버런트라는 그 반향, 그 소리하고 다른 원래 모드하고 맞았을 때 그런 경우가 중요하다.
The singing rod for aluminum is that the same kind of intensity which is still present when the source is shut off in a hall, when all people have gone, that noise is disappeared, then in the same way, the noise which is left over in the aluminum rod when we excite help already when we next strike along, and helps to get the whole performance, the sound of the rod started. So that is now the connection to the loudness of the singing rod, and might be an explanation because essentially the problem has not yet been solved. Thank you for your attention.
오늘 다 말씀하셨는데, 그러니까 이 빛에서 소리는 원래 작아야지만 여러분들이 듣다 보면 어떤 경우는 소리가 되게 커지잖아요. 그게 이제 디렉트 사운드가 처음에 나오고 그 다음 사운드들이 서로 조화를 하모니를 이뤄서 소리가 나오는 게 해석할 수 있는 분명한 또 호시가 되는 방법이고, 그래서 여러분들 경청해 주셔서 감사합니다.
I do agree that the singing rod is one of the most spectacular phenomena in acoustics after all its perfect lecture, but I'm seriously curious about the practical uses of the singing rod. Please explain to me.
Practical application.
Application, yeah. Yeah, application is a bit of a weak point. Not many applications, not many applications. There are some ideas around, but at this stage I can imagine even if somebody has a good idea, he would hold back and make a patent, which I would also recommend to him to do that. Now the field is rather still open, not so many applications yet. I mean, there is a suggestion, for example, to build a new music instrument based on the singing rod phenomenon. So how it exactly works, I don't know, but this is an existing patent.
How did you come up with the idea of the singing rod? Like, I would agree how you decided to, like, this is so interesting, so I would just study about it, right? So I would be able to ask you, how you decided.
You said, you asked who came up with that idea about the singing rod. You can look it up in the internet and find out who was the first to do that. I think it's not quite clear, but now it's well established since about 5 years. There are various citations in the internet, and but there is no person who can be said to be the inventor of this. Various people tried it at about the same time. It is only published in the internet, but no refereed full paper or only one. So it is something worthwhile to do if you want, as a young person, you want to gain publications. That's still an open field, and you can do it at home. I find that quite interesting.